still going. Good. Acid-base balance is a bit of a challenge, and it's possible that you might not get it all, but I do have to try to go through it and at least give you a taste of what's going on. So this is the intercalated cell, and this guy's set up basically to get rid of hydrogen ions in an acidosis. Okay, so if you've got an acidosis, it's equipped to pump out lots of hydrogen, and then the hydrogen can combine with the phosphate and get excreted. There is also, perhaps a little more unusual, there is a B-type intercalated cell. Okay, and this is a situation where it's a little rarer. But it's a cell that looks like this. So this is still lumen over here. What it looks like is a cell that's got the opposite polarity of an A-type intercalated cell. Okay, it actually isn't, because now in the distal tubule, most of the bicarbonate is by exchange like that. It isn't, because this pump is not the same as this pump, even though it looks the same. So from a functional standpoint, it's like flipping the cell around with a different polarity, but it's not actually quite that. So why would, and you can fill in all this part of it. So why would we need this? Well, this is a cell that's geared up to excrete bicarbonate. And so, presumably, if you have an alkalosis, you might need a special mechanism for getting rid of bicarbonate. And indeed, if you have a lot of bicarbonate, you can actually get rid of more. But you know, in a metabolic alkalosis, you get a lot of bicarbonate filtered anyway, and you probably don't need to make this thing happen. Okay? Because if you filter a lot of bicarbonate, you'll actually excrete bicarbonate. However, in a respiratory alkalosis, okay, so you have a respiratory alkalosis, you're blowing off too much CO, so the hydrogen ion is going in this direction, and so actually the bicarbonate is not going to be high, it's actually going to be lower. And so now you have a respiratory alkalosis, and you have a low filtered bicarbonate, slightly low filtered bicarbonate. How can the kidney excrete the bicarbonate? Well, it might need this extra mechanism to actually actively secrete the bicarbonate. So in a respiratory alkalosis, where this is actually low and there's a low filtered bicarbonate, then you might need to turn this cell on to actually actively secrete the bicarbonate, and thus increase the bicarbonate excretion. Make sense? I think that in terms of probably what you need to remember, just remember that the B cell exists. It's sort of the opposite to an A cell, and it serves the function to get rid of bicarbonate. And if you got that much, you're most of the way there. Okay. Oh gosh, I feel bad. You should never tell people that this is a little harder, should you? You're not laughing at me. No, okay, I'm sorry. Okay, so we dealt with a way to get rid of acid, and here we dealt with the right way to get rid of bicarbonate. However, we have an additional system that helps us to get rid of acid. Okay, the phosphate system by itself doesn't have enough oomph. That's spelled OOMPF for notes. Sorry, I'm getting a little punchy too. So we need another system that helps us to get rid of acid. And it's there on page 7. And as you can see, it's just a little bit more involved. So I think what I'll do is, in this case, the title says acid excretion is the same as adding new bicarbonate to plasma, which is what we said before. But in order to get rid of the acid, we need to trap it, in this case, with ammonia. Okay? Before we trapped it with phosphate, and now we're going to go through a mechanism where you can trap it with ammonia. So if you look at the, let me guide you through these diagrams. Let's start with the top left, which is the proximal tubule. And this will be the easy part to understand. So in the proximal tubule, this is the lumen. Glutamine can be filtered, and actually it can also be secreted. And I think it says that on the diagram. And so you get glutamine inside the proximal tubule cell. The glutamine can be metabolized in the proximal tubular cell to 2NH4 plus 2HCO3 This will go this way. Remember, mostly by that sodium bicarbonate co-transport. And this guy can actually take a ride on the sodium hydrogen exchange 3 pump, the same one that pumps protons. But in this case, the ammonium can take a ride on it. It's basically protonated ammonia. And so you can actually effectively excrete protons by this mechanism. you generate the acid ammonia or acidified ammonium, and you pump it out in much the same fashion as you did before, but the ammonium can't be reabsorbed. Remember, if it combined with bicarbonate, it got reabsorbed. Okay? So here, you made ammonium, it can't be reabsorbed, and so you got acid in the tubule right here. Oh, and by the way, we added new bicarbonate to plasma, which is consistent, right? We wanted to get rid of acid. It's the same thing as adding bicarbonate to plasma and excreting the acid. Let me say that again, and I'll read it directly off here. Acid excretion is the same thing as adding new bicarbonate to plasma. You get rid of the acid, and you make bicarbonate. Okay? So it looks like we've done all the work that we need to. However, what happens is that ammonium, if we just got rid of the ammonium, everything would be wonderful and it would solve all our problems. However, the ammonium gets reabsorbed in the loop of Henle. And there are several possible mechanisms. It can take a ride on the sodium chloride potassium transporter. It may be transported directly. But whatever, it is reabsorbed in the loop of Henle. And much like sodium, because there's a countercurrent, the ammonium accumulates in the inner medulla of the kidney. Okay? And you're saying to me, oh gosh, why did we get complicated? We just needed to pee it out, right? Well, so it's accumulating in the inner medulla, which is the bottom left diagram. And then let's go to the bottom right diagram. So now we're in the intercalated cell. So you got NH4 in the interstitium, and that can generate ammonia, albeit not a lot, but the ammonia can now diffuse through to the lumen, and there may actually be ammonia transporters too, but it is a gas, and so the conventional idea was that it just passed from here to here, but there are probably transporters. So the NH3 comes to here, and remember, you're pumping hydrogen ions like crazy out of this intercalated cell, and that then combines with the ammonia, and the NH4 plus can't be reabsorbed. It's what's called diffusion trapping. The ammonia diffuses through here, traps that hydrogen ion, becomes ammonium, and gets peed out. Okay? So it's a little bit more complicated than you would like it to be, and I understand that. But that is the mechanism. I think that's in Costanzo that way. That diagram is not from Costanzo, but I think she explains it in a similar fashion. So in other words, we can get rid of acid as ammonium, but it's not quite straightforward. Yes? Yes, ma'am.
Do you mind explaining why the ammonia can end up in the medullary interstitium?
Okay, so the question is, how can the ammonium end up in the medullary interstitium? And it's the same thing that we did when we concentrated sodium in the inner medulla. Okay, anything that gets reabsorbed in the ascending loop of Henle, by virtue of this countercurrent thing, will tend to get concentrated in the medulla. Just the same as sodium that we did yesterday.
So there is a transporter that transport that out into the medulla, otherwise it's not going to end up in the medulla.
Yeah, and I didn't. So it's the diagram on the. Is it top right? That top right diagram is the ascending loop of Henle, and you will recognize top left part of the diagram, a sodium 2-chloride and ammonium transport. That's the same as the sodium 2-chloride potassium transport. So ammonium supposedly can take a ride on the potassium site and get reabsorbed. And then it shows some other mechanisms for reabsorbing sodium, reabsorbing ammonium. But and we're not responsible for the mechanism. We're not worried about the mechanism. We just need to know that it does get reabsorbed in the loop of Henle. Okay, so don't worry about the fine mechanism. It gets reabsorbed. Okay, and by virtue of the fact that it gets reabsorbed by the countercurrent principle, it has to get concentrated in the medulla. Okay, same principles that we went through yesterday. Okay. So, I actually have an explanation as to why it's so complicated, but I think I'm not even going to try to tell you. Can you live with that? If you're interested, I would be happy to discuss it with you afterwards. I just feel that there are certain things that I need to explain, and then there's certain things that I probably just need to let go. But if you're curious, I'm more than happy to go through why I think the mechanism works this way. Okay. So let's flip the page. Okay. Okay. Measurement of acid excretion. We're on page 8 now. So you can quantitate, and of course exams might want you to do this. You can quantitate net acid excretion, and it's quite simply the titratable acid plus the ammonium minus the bicarbonate. Now, titratable acid, so you measure these things in the urine. And I think it's pretty clear that if you titrate back to pH 7.4, that's the titratable acid. That's mostly phosphate and some sulfate. Okay? So the problem is that a lot of protons are got rid of by ammonium, as we just described. But because the pK is about 9.1, 9.2, you can't titrate that back to 7.4, and you actually have to measure that separately. Okay, so the acid is that plus what you can't measure as titratable acid. And minus the bicarbonate. Usually that's very small. Costanzo, I think, doesn't actually mention the bicarbonate, which I suppose is justified because in this particular case, if we're looking at an acidosis, it's going to be small anyway. But theoretically, technically, you should subtract the bicarbonate. So, you're M1 medical students. You know that somebody's going to ask you to make this calculation. Does it have any clinical relevance? Yes, it does. Okay. So, particularly for renal tubular acidosis, where the defect is in the distal tubule, and that's renal tubular acidosis 1, type 1. One of the problems is in a type 1 renal tubular acidosis, you have an inability to get rid of acid, but the GFR is usually pretty close to normal. And so in order to diagnose a renal tubular acidosis in the distal tubule, you need to get a measure of how well the kidney can excrete acid. So what you do is you give an acid load and you measure how much of that acid load is excreted in a given time. So it does have clinical significance. Okay.
So are we saying that if a patient who has a renal type 1, then the net acid excretion gonna go down?
Yes. So the question is, if you have a tubular defect in the distal tubule and you can't get rid of acid, then it will be reflected by a reduction in the net acid excretion. Okay. Yes. Yes. Okay. So item 4, I've just put in some net acid excretions and kind of added the components there. So for a normal person, excuse me, who's producing fixed acid at 50 millimoles per day, of that 50 millimoles, normally you get rid of it as 20 millimoles of phosphate and about 30 millimoles of ammonium. In a diabetic ketoacidosis, you make lots and lots and lots of acid. And in this particular case, it's saying you're producing 500 millimoles of acid. In that particular situation, you can get your titratable acid up to about 100, but that's about the limit. And so in order to deal with this rather profound acidosis, you have to step up the ammonium production. And indeed, you can increase glutamine metabolism quite profoundly. And in this situation, you get rid of up to 400 millimoles of acid as ammonium. So chronic renal failure, so now we're back to a normal diet, and we're producing 50 millimoles of acid. But in chronic renal failure, remember, you've got reduced flow rates, so secretion of things gets to be difficult. And so, at least in the short term, you can't excrete much as titratable acid, and you can't secrete much or excrete much as ammonium. And of course, those are imbalanced and you get an acidosis. Okay, look, we're going to do one more page and then we're going to stop for the day, because I recognize that this is a struggle. Okay, so let's do one more page, and the next page is not horribly difficult. Let's talk about how we regulate hydrogen ion secretion. So assuming we have an acidosis, let's say it's a respiratory acidosis. I don't know whether I've still got diagrams up here. I don't. But if we have a respiratory acidosis, we generate a lot of carbon dioxide, and in the cell, you've got a lot of carbon dioxide which gets into the cell, and the carbon dioxide makes carbonic acid, it makes bicarbonate and H+. The H+ goes out, and you drive the renal secretion of hydrogen ion when you have a high CO2. And, and understand, one thing that I probably haven't been very clear of is that if we have a respiratory defect where we've got too much CO2, ideally we'd want to fix the respiratory defect, right? But that's the primary defect. And if I just keep accumulating CO2, I'll get more and more acidotic, and eventually I'm in trouble. So we have an ability, when the respiratory system screws up, the kidneys can actually compensate. So when there's too much CO2, the kidneys can compensate by getting rid of this surplus hydrogen ion. Okay. Conversely, if the kidneys are incapable of getting rid of acid, we can actually increase our breathing and blow off CO2 and compensate for a kidney defect by hyperventilating. Okay, and we're going to tackle that on Friday. Okay, so that kind of explains that. So next, the filtered bicarbonate. So let's assume now that we have a metabolic defect. We just chug-a-lugged a bottle of hydrochloric acid. Okay. We took on too much acid. It combined with the bicarbonate and went this way. Okay. So if we got a lot of acid, it'll combine with the bicarbonate, and so the bicarbonate will go down. So if this goes up, it'll send the reaction in this direction, and this will go down. Okay, so there's a certain amount of automaticity that operates here. So the bicarbonate went down, so the filtered load of bicarbonate goes down, and so all that hydrogen ion being pumped out in the proximal tubule will exhaust the bicarbonate real quickly, but you keep pumping that hydrogen ion, it's going to have to combine with something else. Oh, how about phosphate? Okay. So what I'm saying is there's a certain amount of automaticity. In a metabolic acidosis, the bicarbonate will be low, and that means that the hydrogen ion will combine with something else, which will get peed out, which is a good thing. And then the respiratory alkalosis is basically the reverse of what we just described with the acidosis. Two or three extra things. Hydrogen secretion is stimulated directly by hydrogen, by pH, or at least acidity in the ECF. So you can actually turn the system on. Glutamine synthesis in the liver is turned on in an acidosis. And so that makes sense. You make more glutamine, it arrives in the proximal tubule, and it can generate ammonium. And then finally, so acidosis can actually stimulate parathyroid hormone, which can then cause phosphaturia. So in some ways we should probably continue, but I think that's enough for one day. So here's the plan. On Friday, we'll come in and we'll do the blood gases, the next 13A, I think it is, and that should not take, probably not an hour. Okay. We'll take a break, and then somewhere around 11 o'clock, I'll do a review of the whole renal section. Okay, it will be fast because you have a test coming up, yes? And you didn't want to hear that, did you? Okay. My philosophy is that I need to protect your time as much as possible, and if I just stand up here and talk forever and repeat everything that I've repeated in the last 2 weeks, that's not an efficient use of your time. So I will try to motor through it, and I think I can motor through it, point out what I think is significant and what you should remember, and I'll use PowerPoints, okay? So I'll move through it really quickly. So that's the plan. Any thoughts, complaints, suggestions for doing it differently? And hopefully we won't need to do anything in the afternoon on Friday.
Can you post that review PowerPoint on D2L so we can write notes on it if we want to?
I don't know. Can we do that, Dr. EK?
Absolutely.
Do you have it?
Once you give it to me, I have it.
You're not going to give it to you? Oh gosh darn. Yeah, I'll give that to Dr. EK. So the second thing is office hours. I'll be in my office tomorrow between 7 and 11 and between 2 and 5. So those are office hours. And I would be happy to talk to you. Okay, let's stop. Oh, question.
Did you write the questions on D2L?
Can I write the questions on D?
The quiz questions on D2L, the assessments.
I don't think I understand the question. Do you understand the question?
There are assessment quizzes on D2L.
There are quizzes on D2L, yes.
Did you write them? I'm going to just see not since you don't know what they are.
Oh, did I write them?
Yes. Are they reflective of the exam?
Are they reflective of the exam? Partly. Okay. So the quiz questions, I'm thinking that they may be a little easier than the exam. I mean, they're pretty straightforward, the quiz questions, aren't they? They're mostly to get you up to speed. But yeah, I think the exam might be a bit more challenging. Some of those questions are really easy, aren't they? Aren't they? Have anybody done them yet? Oh, shame on you guys. Oh, shame.
Can you post additional questions that are more reflective of the exam?
No. The questions that are up there. And if you want to get exam questions, you can go through, there's a whole bunch of shelf type things that are out there. But no, I can't write a whole bunch of new questions for the exam. Okay? I mean, I just don't have time. Just don't have time. Okay. All right.